Hi everyone, this video is dealing with a special little equation that we've got in Trig here, or a little function, a cos x plus b sin x. Often it's really handy to write trigonometric functions in this format, and so I'm going to take you through this last little bit in the trigonometry unit. If we drew the graph of 4 cos x plus 3 sin x, you get this. Now, if you look at it, you'll see pretty quickly that it looks kind of just like a cos graph or a sine graph. In fact, when I look at this one, I think of it, it kind of looks like a cos graph. It's been shifted across about 40 degrees, and the amplitude looks like it's 5. You know, so I can kind of guess that this cos graph is kind of maybe that equation, 5 cos x minus 40. So what we're going to try and do is start with functions like this that are the sum of two trig terms, and then we'll end up with so that they're just one with one trig term, and that's really helpful if we're trying to solve equations particularly. So if we're trying to find, solving when this is equal to 2, it's much easier to do this equal to 2. So that's what we use this technique for. So the method is, we're going to find an exact method for finding out if 4 cos x plus 3 sin x equals something r cos x minus alpha. So we've shifted it across and we've changed the amplitude. We want to find the values of r and alpha in that equation there. Okay, so remember the trig addition formula. We know a formula for cos a minus b, which is that formula there. So the right hand side of that equation becomes that. So I've just replaced the a with x and the b with alpha, and I get that equation there. Now what I do is look at the left hand side and the right hand side, and I'm going to just compare the coefficients. Alright, so you can see on the left hand side the number in front of the cos x is 4. On the right hand side the terms in front of the cos x are r cos alpha. So those two things must be the same. Okay, so if we do that for the sine values as well, the number in front of the sine x on the left is 3. And the terms associated with sine x on the right are r sine alpha. So those two things must be the same. So we do that and we get these two equations. Now we just need to solve these equations. There's two equations and two unknowns. We're good at solving equations. So simultaneous equations, easiest way here is just to divide. I think that's the first step. Divide the second equation by the first equation. Then the r's cancel nicely. On the right hand side we get tan alpha. So I wouldn't have gone 1 divided by 2 because then we would have had cot alpha. So this is just easier if you do the sine divided by cos. So tan alpha is 3/4. That is infinitely many solutions to that one, but we're just looking for the one between 0 and 90 normally. So the first one. So in this case 36.9. Once we've found that one, the way that you find r is go back to those first two equations, square and add. Now why would squaring and adding help us here? The reason is when we do that, on the right hand side, we factorize r squared, we get cos squared alpha plus sine squared alpha, which we know is equal to 1. So therefore we get r squared is 4 squared plus 3 squared, so r is equal to 5. So now that is the exact situation for 4 cos x plus 3 sin x. Let's apply this now to an equation. Have a look at these two equations here. Which one's easy and which one takes a lot more work? Well, the one that's easy, let's look at a. If we just divide everything by cos x in a, look at what we get. Cos x cancel, sin x over cos x is tan x, and on the right hand side, importantly, 0 divided by cos x is always 0. So we get a nice equation in tan. We've got shift tan negative 4 over 3. This is a simple equation that we can solve. However, in part b, if we divide everything by cos x, not so nice. On the right hand side, 2 divided by cos x is not 0 anymore. We've got 2 sec x, and we're no better off. Okay, so we need another method for solving equations like b. And the method we're going to use is this one that I've just shown you. Okay, 4 cos x plus 3 sin x equals 2 just becomes that. Now we divide by 5, take the inverse cos of both sides, and we can go from there. So I'll just say the last step, inverse cos of both sides there, and then we're going to add on 36.9 to get the solutions. So here's an example of using this form to solve an equation now. So 5 cos x plus 12 sin x equals 10. You can see dividing by cos x here is not going to help us. No good, because on the right hand side we're going to have 10 divided by cos x. No good. So the way that we're going to do this is we're going to write it in that form there. Now just note that we could have chosen r sin x plus alpha or r sin x minus alpha. It doesn't matter. In the end you're going to get the same answer anyway. So we've just chosen the same one, so we expand the right hand side, and now we're just going to compare the coefficients. On the left hand side there's a 5 in front of the cos x. On the right hand side there's an r cos alpha in front of the cos x, or associated with the cos x. So we get that equation. Same for the sin x, and we get that equation. Divide the two equations and solve 67.4 degrees. Once again, we're only interested in the angle between 0 and 90 to start with. And r is going to be the square root of 5 squared plus 12 squared. And that little shortcut always works. If you look at the coefficients of these two terms, square them, add them, take the square root, just kind of like Pythagoras' theorem, and that gives you the value of r. So now, the equation goes from that to that. And here is an equation we can solve. This one here, not so much. This one here we can. Divide by 13. Take the inverse cos of both sides. We'll call that theta if you like. And we get theta equals 39.7. Don't find x at this stage. We've got cos of theta, or cos of x minus 67.4 equals 0.769. Okay, so we've got to be really careful here. Same as the ones that we had where we have got cos 2x equals something. We need to find all the angles where 2x is equal to a certain value. Okay, so in this case we're looking for angles between about negative 67.4 and 292.6. I don't worry about that for now. I'm just trying to find the correct angles. So you can use the unit circle, or you could use the cos graph to kind of see where the solutions are happening. And those two there are the ones that we're going to be interested in. Okay, so x minus 67.4, this would be my next step in the working, is 39.7 or negative 39.7. Adding 67.4 to both sides gives us 107.1 and 27.7. That is the answer.